a tutorial on the big data management system, Apache AsterixDB, and specifically on JSON Analytics with AsterixDB. So this will be a live Zoom tutorial, and it will be presented by Mike Carey, who, by the way, is one of the founders of BOSS, together with Ian Maxon, Till Westman, Dmitry Lichangin, Fanwades Sinhong, and Glenn Galvizo, a team from UC Irvine and Couchbase. So Mike and Tim, the floor is now yours.
All right, so let me try to screen share. Let's see, right now it's, yep, we're good. I will go here, I'll move Zoom, I'll say present, and we should be good to go. So can everybody see okay? All right, yeah. So we're going to be talking about JSON Analytics with Apache AsterixDB. And again, this is a team from UC Irvine and Couchbase. Actually, the project spans a number of other institutions. We've had contributions from significant from Riverside, UC San Diego, and people elsewhere. But this is kind of the delivery team. And we're going to do a kind of a marathon thing where we hand off the baton. So I will start, and then I'll hand the baton on to someone else. And we're going to do that and run through almost everyone. Glenn is our TA, and he'll be monitoring the question streams and letting us know if there are questions so that we don't miss answering them. All right, so this is what we're going to do. We're going to give you an overview of Apache AsterixDB, and that's my job. Then we're going to get you connected to some instances up in AWS so that you can play, and you'll be given some assignments to do during this tutorial. And then we'll do kind of a two-part coverage of how do you use SQL++, which is an extension of SQL for JSON, to query and analyze JSON data. We'll give you kind of the basics, what's different from SQL and how does that look, and then how do you do sort of the basic things like grouping and aggregation in SQL++, and then we'll move on to some of the more advanced analytics, show you how to do things like grouping sets, rollups, window functions, and so on. And all of that will be interactive, so you'll have a chance to basically play as you go, and you can do it, and we'll give you some lab time and answer your questions and so on. And then at the end, we'll give you a demo of some stuff that's futures related to incorporation of machine learning models in AsterixDB. All right, so what is AsterixDB? It's essentially a parallel database for NoSQL data, for semi-structured data. And so the wish list for something like this, at least as far as we were concerned, is you want to be able to manage data. So you'd like to be able to kind of own the data, index the data, and use sort of the usual database optimizations on the data. But we need to be flexible about the data model. So we wanted to deal with semi-structured data a la JSON, as opposed to kind of strict tabular data with schemas. Want full query capability so that you can do all the kinds of good things that you used to do declaratively using a query language and interact with your richer data that way. Be able to continuously ingest data because that's where big data comes from. Under the hood, you want parallel query processing. If you're trying to do analytics over a large volume of data, you want to do it right. You want to use kind of best practices from parallel databases to do that. And you'd like the cost of that to be proportional to the task at hand. So you don't want to have to kind of scan all your data for every query. You want to have things like indexes and so on. And then in addition, it's JSON data. It's 2020. People have points and they have points in time, points in space, they have text, and you'd like to be able to have more rich data types to deal with that. And so we thought about that about 10 years ago and said, how would we address this problem? Hadoop is not the answer. We want to do something different. And so we're going to take ideas from semi-structured data management, ideas from best practices, parallel databases, Teradata, DB2 Parallel, Microsoft Parallel Data Warehouse, and things like that, and ideas from the Hadoop world, and bring that all together and think about what would the next generation of database look like for semi-structured data, in parallel, relaxing schemas and so on. All right, and we also talk about big data, and people talk about it in different ways. Just to kind of clarify our point of view, big data is data that doesn't fit in memory on a cluster, right? So big data is data where, a lot of that data is maybe older, and it shouldn't all be kind of sitting in memory. So big data is, we're still assuming that data is much bigger than memory. All right, so just a few things about under the hood that are not entirely relevant to the tutorial, but just to give you an idea what the system is. It's basically a parallel database system. So for those of you who are used to looking at them, we've got a bunch of nodes, and each node has storage and runtime, and there's a query compiler, right? So it looks essentially, as from a high level, the same as a parallel database would look like. And we won't go into the details here, but basically SQL++ talks to this cluster, which then is basically doing your query processing on a cluster, and you can scale this out horizontally to make your queries run faster or to deal with more data and keep your query response times kind of the way you'd like them to be. And so it's a parallel database under the hood. And if you go further under the hood, just to give you a little sense of how storage is managed, we have an LM-based storage system. Everything is LSM everywhere. So there's a primary index that your data lives in. So all of your records are stored on the primary index, indexed by their primary key. That's the home for your records. And then there may be a bunch of other indexes, a primary key index, a secondary index on this field, a secondary index on that field, and so on. And the data is partitioned across your cluster. So you have some number of nodes in your cluster. You have some number of I/O devices on each node, and each of those is a partition, and you can scale things out. So each of the storage partitions basically holds, sort of a shard in 2020 terminology of your data. Under the hood, the data objects are in a binary format for semi-structured data that we call ADM. It's not sort of stored as textual JSON. We have indexing. You can have B trees, R trees, or text indexes. And people talk about global versus local indexing. We do local indexing, which is to say that all of the data that an index on a shard is talking about is the data that's stored in that shard. And so that's the sort of the indexing architecture under the hood. And again, all that's just to kind of give you some background for what's under what you're going to be running. Okay, so let me just hit here, and then I can advance. So what I want to do next is give you sort of go over the hood and say, what does Asterix data look like? And so this is just a little example that we're going to be using throughout the tutorial. And so what we've got here is, first of all, we have to have a place to store the data for a given application. So we're going to be talking about a toy application that we actually used in our 400+ student class basically last spring, called Shop a Lot. So this was kind of a COVID area shopping thing where you could kind of have gig workers go and shop for you and they'd meet you in the parking lot. This is a subset of that data. So it's a little shopping application with users and data and products and things like that. So the first thing we're going to do is create a dataverse because it sounds cooler than database, called Shop a Lot, which is going to be a place where we can store our data. And then the next thing we're going to do to build out this sort of hypothetical company is we're going to tell the system, the things about the data that we want to store. And so this is an example of a data type in the Asterix data model for users. And a user has a user ID, it's a string, and an email address, it's an optional string. So, nullable is question mark. And then this is semi-structured data. And one aspect of semi-structured is it doesn't have to be flat. So we can have a nested record for name, and we can have a nested array of records for phones, right? So we can record multiple phone numbers for our users. They might have a mobile phone and a home phone and an office phone and so on. And so that's the description of a user in our data model. And then this is a description of where we want to store it. So we're going to create a data set called users, and the stuff inside will be of users type. If we wanted to have multiple data sets of users, we could. We're just going to have one for this application. And then we can start sticking some data in, right? So we insert a user and we capture the information about that user. And notice that we had a couple of optional things here. So email is optional. So not all users are going to have an email address. Not all of them will have phones and so on. But this one happens to have both of those things. So this is an example of a JSON record, or actually an ADM record, kind of the same thing. JSON is like ADM is a superset of JSON that we can now insert into that data set. So that's one aspect of kind of having this semi-structured data, which is it doesn't have to be flat. It's kind of richer in its structure. The other aspect is come as you are, right? So there's a type knob in AsterixDB, right? You can decide to say all of that stuff. So for those of you who are schema bigots and you like schemas, we've got an answer for you. But you can also turn the knob and dial down on typing, right? So instead of having to say all of what we just said, you could actually simply say, I'm going to have users and they're going to have a user ID, right? I'm going to have a data set of users, and you could insert that same record into that data set of users. So you're not required to provide a schema. The benefits of providing a schema are that when someone wants to query the data, they can go look at the schema and go, oh, cool, I know what to expect. Or if you would like, the information in that schema to be true of all the objects in your collection, will maintain that for you, right? So you can think of it as an integrity constraint on your data that you can optionally provide and will optionally enforce. But otherwise, you can just say, hey, users have a user ID, and here's the rest of my data. I'll insert that data, and everything you do in this tutorial would work either on the data set with all of that type description, or on the data set with just this type description. So it doesn't change what you can ask in queries. It just changes like kind of the restrictions on the data that can live in that data set. And if you really, don't feel like doing anything up front, turn the type knob again. I don't want to provide a user ID. Don't make me do that. You could actually say, okay, so, there's a user ID. It's going to be a UUID, and I want you to generate that for me. And here's the rest of my data. So you have some type options that we just wanted to kind of make you aware of. All right, so shop a lot. What else do we need? Well, we're going to need to have stores, right? Because the idea is that these gig workers are going to go, you're going to place an order and they're going to go to that store for you and they'll meet you in the parking lot, right? So we're going to have stores with a store ID and name, and again, some nested data, phone, and maybe a set of categories, right? So the store might have, baked goods, and the store might have baby goods and things like that. So this would be the categories, multiple of them that a given store might have. And then we'll create a place to store our stores that will overload the term store. And then we'll also have products, right? Because you want to buy stuff. And so they'll have a product ID. A given product will be in a category. It'll have a name and a description. And you don't have to say everything about an object's type, even if you're using some of the typing stuff. So, there's going to be a price, a list price in the product records, but we didn't happen to declare it here. And you might want to say the list price is optionally a float. And later on in the tutorial, you'll see what the benefits of having said that would have been, because we're also going to take a little time and talk about how do you deal with kind of dirty data and data types and things like that when we go through the tutorial. And so now we'll create a place to put your products. And then you're going to want to be ordering stuff, right? So we're going to have orders and line items, right? So here we have orders, or order ID, user ID, store ID, total price, time placed, all required. If a user wants to, when they place an order, they could say, hey, I'd like to get it at this time. That's optional. And then once an order has been fulfilled, it has an optional fulfill time, because while it's open, it's not fulfilled yet, but then that time will appear. So we'll see some orders kind of at the end of the data set that haven't been finished yet, and they'll be missing that. So these are two pieces of information that might be missing, like you might have one or both of these in your data. So again, semi-structured, has the possibility of missing data. Those fields would just simply not be there. And then, of course, we're going to have line items, right? So we're going to have item ID, quantity, selling price, product ID, the usual stuff for e-commerce, except that items don't have to be orphans, right? So we don't require them to go live somewhere else. They can be inside the order, right? Because we have nested data, right? So this is kind of what orders should look like when you store it in an application database. And then we're also going to need to know, like, what can I get where? So stock information, this product, this store, in this quantity, that's what's in stock right now. And we'll have a place to store that. So this is all, again, to kind of give you a sense of the data model, but also the data that you're going to be playing with in the tutorial. This is the schema for that data. So we're showing you the schema version so you can really understand what's going to happen there. So again, just, what does the data look like when you sort of get it back from a query? Some of your orders might have a time fulfilled. Some of your orders might have a pickup time, no time fulfilled, and so on. So that's just a brief introduction to the data model. What we're going to do is spend most of the time here on the query side. So we're going to have a whole bunch of this data, not as a ridiculously large amount, but not a ridiculously small amount, and let you play around with that. Okay, so what we're going to do is give it a try. So we're going to get you set up next. I'll hand off in just a second to Ian, who's an AsterixDB staff member, who will show you kind of how to connect to the system. And you're going to be using this highly sophisticated, carefully designed user interface, which is there's a white box. You type your query and you hit run, right? Works for Google, works for us. And we'll get you kind of using some options. We'll suggest that you use SQL++ as a language, because that's the only one we support anymore. We'll suggest that you use JSON formatted here so that you get to see your data kind of looking pretty like that. All right, so what I'm going to do at this point is let Ian grab the screen. And I think you can do it without me stopping sharing, but if not, let me know and I'll stop sharing.
I think it's a little bit different. I think you have to.
Okay. All right. I'll stop sharing. Your turn.
All right. Cool. Thanks, Mike.
Yep.
All right. So I posted a link in the chat and in the Slack. So basically, to start with this demo, everyone's going to get their own instance. And it already has all the data that Mike was showing preloaded. So should all be good to go. And so to access the instance, basically just go to the URL that's in the slide, but also in the chat and also in Slack, the tahunga/roundrobin.php. And it should just redirect you to an EC2 instance. And you should see the beautiful AsterixDB query console, as Mike mentioned. And also on the slide, you see here, there's a really basic query, just a simple, very simple query, just to test it if you'd like. So there's also a link in the chat for a poll. So please fill out that poll once you've either gone and got your instance or if something's going wrong. So we have an idea of, so we're sure if everyone's set up or if there's issues. So if something is wrong, please let me or any of the other presenters know here in Slack, in the chat, wherever, and we'll hash it out. We'll get it sorted for you. And so, yeah. So I guess everyone gets set up and we'll take a look at the poll.
So Ian, I don't know if you can share the poll so we can see how people are doing.
Of course. Go ahead.
So I encourage everyone to play. So I have to admit, I watched the Spark tutorial. It was fun to watch. I didn't play. This will be easy to play with, and so people should get set up and play. So don't just, I mean, you can just watch, but it will be more fun if you play, and you'll have an opportunity to sort of interact with the system, and it's super painless to play. All right, good.
Giving my F5 key here a workout.
All right, I guess we can move forward. And if you have trouble, if you're still wanting to get connected and you're not able to, again, Slack us or chat us, and we will take care of you.
Yes, please. And if you have any other, if any of the, something strange happens to the instance during the tutorial, you notice any sort of like exceptions or something that doesn't seem how it is, please, again, let us know and we'll get it fixed. All right, so I'll go ahead and hand it off.
All right. So let me see if I'll be able to share my screen.
And this is Till Westman from Couchbase.
All right, so let's see if I can do this. Okay, yes. So my big challenge right now is that I don't have the Zoom window in my view. I'm not sharing right now, right? Can you hear me?
Yeah,
yes, you're not sharing.
Okay. Here we go. Now, can you see it?
Yeah.
Ah, all right. I'm sorry about that. All right. Okay. So yeah, after Mike gave the introduction and told us a little bit about the system and about the typing of the system, let's start and look a little bit at what the language looks like. So the language is SQL++. It's a generalization of SQL. However, it can also live kind of with the type system that we have. So, and we'll talk a little bit more about what that means. So let's first start with kind of the basics. So in general, I mean, it's much like SQL. I mean, the goal is to really be like SQL to make it amenable, while still allowing to manage data that doesn't have a schema and allowing to manage data that is has nesting. But let's start with a very simple example here, right? We have we have the user's data set, and we want to get all of the user IDs of people who have a Gmail address, and we just take 3 of those, and so you have this query that looks exactly like SQL, and you get a result. So the output looks a little bit different than what you would be used as a SQL user, because it's all in JSON and with curly braces around it, but basically it's exactly the same thing. You get these 3 objects or records with 2 fields, and so the user ID and the email, and you get 3 of those. So that's all very simple. Another simple query would be this little join over here. So what we're doing is we're wanting to get the email and the time an order was placed for orders that have a total price of larger than 200, and we want to get the top 3 of those. And so this, you look at the query, and this looks all very much like SQL. And you get similar way the result, right? This is just very simple. Again, 3 records, 3 objects with the email address and the time when the order was placed. Of course, I mean, it also works, in the kind of in the other style of writing joins. If you're a little bit younger and you don't like the commas and you like the join clause in there, then we also have you covered. So again, nothing spectacular here. And then, of course, we also do our grouping and aggregation. We'll talk more about details later, but again, a simple query here where we want to get basically the number of orders per store that we have, and we only want those that are larger, that have more than 0 orders, okay? And we want to again have the top 3 of those. So this is the query at the bottom left. And again, right, this looks like SQL, this works like SQL, and everything is fine. However, not everything is always the same. So we have this query. We had very similar one on the previous slide where we join the users and the orders, and we want to get the total order price above 200. However, if we run this query, which is perfectly fine SQL, the system will be unhappy with us, and it will tell us that we have a problem resolving an ambiguous alias reference for the identifier total price. And if you see on the left side, the total price that is in the where clause, and we just ask for the total price being more than 200. However, we don't have a schema. And since we don't have a schema, the total price field could be a user's field or an orders field, and we didn't tell anybody about it. And so we can't really resolve that. So there's a simple solution for that, which is what you would anyway do, I think, if you write nice SQL, which is you provide the aliases, right, as we did here. So we gave a U alias to users and an O alias to orders, and then we can specify that the total price is actually an orders field, and then we can also run the query. But basically, this flexibility that we're gaining by not having a schema has a price, right? It's that you can see here. And there's another thing that's somewhat different, and that is select star. So what do you usually use select star for? Often you do it, you get a new table and then you do select star and get the first n records to find out what's in the data, or you just get a description of your table which has the schema, but of course we might not have a schema. So in this example, we don't have a schema, and so we don't really have the option of looking at the schema. We'll need to look at the data. And so what select star does is quite different in this case, and which is, given that it's exploratory and you really want to understand what's happening, we're giving you a record that has an intermediate layer, basically an intermediate level that you see here with which materializes the variables that you're using. So what you're getting here, you're getting the output of this query, is you're getting, of course, a list or a collection of records, and each of those records here has a U field and an O field, and the U field will contain the complete user object, and the O field will contain the complete order object, as you can see here. And so basically you get all of that in that data, and you're getting these two fields, the U and the O, to be able to disambiguate. So basically there are no name collisions right now, because basically we didn't have name collisions in the aliases. And so basically we don't have name collisions in this, and we can be sure that there are no name collisions when you're constructing this result. So this is quite different, of course, but it's helpful in the context that you can have the schema to rely on disambiguation. Okay, so this was kind of what happens if you do SQL-ish things. So there are also some extensions. One of the extensions is that you can add the keyword value after select. That is there to enable you to actually return single value. So everything that we returned so far with the select clause were objects, full records, right? But sometimes you just want to get a value. You can just get an integer, a string, whatever it might be. And so in this example, we just want to get the product ID from the stocked by dataset, and we just do that for a single store, and the output of that then looks like this. So basically what we got is just the 3 product IDs that were stocked by the store C4 and 2L. So no records in here, just basically a simple sequence, basically of sequence or array of strings. And an interesting other thing that you can do with it is that select value also allows you to apply expressions to your data before returning it. And so in this case, what you see here, you have select value, and then you get the expression. The expression is the object construction that you see on the left. So you have those curly braces, which are an object constructor. And it tells you that you have 2 fields inside of that object that you're constructing, one store name, one quantity, and you take the values that you're getting from the stores and from the stock by data sets, again for a single store ID. Yes, and so this is kind of a way that you can use the select value to bring an expression that is basically arbitrary into the picture, and construct such objects. And this is, of course, you get a result like that, but this is also equivalent to just using a regular SQL formulation of this. So basically, as long as the object constructor basically has 2 fixed strings as field names, you can just basically use them as aliases, take the value in front, put an as, and take the aliases after that, and that is exactly the same. So it's just basically on the left side you kind of see how we internally think about it. On the right side you see basically how you would write it if you write it in SQL. Okay, and another interesting thing that you can do here, and that what we're using it for, is to create nested structures. So in this example right now, again, we're working with the stocked by and the stores datasets. However, what we're trying to do right now is that for a store, we want to get all the product IDs that are stocked by the store. And we basically, what we want to do is we want to actually get those product IDs as an array, right? Basically as a nested collection in the system. And so we just basically have the subquery down here, and the subquery will determine the product IDs. And basically the result of the subquery, actually the result of any subquery, is an array. So basically, if we run this, we get exactly what we're expecting. So we're getting an object that has a store name, that is the name that we got from the store, and then we got the result of this nested query, which are these 3 product IDs. All right. So now that you have learned all about, okay, so now that I've talked a bit about how these things work and what we do about aliases and name resolution, we have a quick quiz right now. And so we want to find out which of the 4 queries that we have here, A, B, C, and D, retrieves the orders that have the highest total price. So we have 4 formulations here. And so I will basically put the exact, oh, yeah, Glenn already did it. So basically we have a quiz in the Zoom chat. So please, if you open that up and then take a stab at which of those things will actually return what we're asking for. And now, when do I know we're done?
We should have planned for music during these downtimes. Glenn, do you want to? Yeah.
So I guess what happens if I just click on it? That's probably not good, right?
I could play the Jeopardy music, but I don't want us to get copyright striked, so.
Oh, that's true. Someone is asking for the correct answer in private. No cheating. This is being recorded too. So. Academic honesty is important. So can we show the result? Let's see what people are saying they think it is.
Yes, let me see if I will share what I share. All right. So should I go to the results now? Are we still voting?
Let's see how it's going so far. B and C. It's evenly split.
We only have
how many votes? Oh, I see. We don't have a lot of voters yet. Maybe we. And people should feel free to just kind of look at it and go ahead and cast a vote. But it's definitely a B or C. All right.
All right. Well, we'll go ahead with 4 votes.
Go ahead with 4 votes.
Sorry? Yes. So, okay.
Yeah, I'd say let's proceed.
Stop the sharing, and let's.
And the good news is this is actually not graded, so it's okay. Quizzes are just an exercise.
Okay. Here we go. All right. So let's see. So we'll just go through them one by one, and then we'll see what's happening. So okay. So the first one. So what's happening here is we run the query. And the result of the query is a type mismatch. And so what does that mean? So what's happening in here? So we're trying to resolve the names. And so what's happening in the second line, we introduce the orders dataset. And with the orders dataset, we kind of introduce an orders alias, right? Because if you don't provide an alias, then basically you get the name of the data set. And which means that the orders variable that you see here on the right is actually bound to a single order, right? Because that was the alias that we got. And then we're trying to select from a single data model instance, and we're really unhappy with that. And so this is that's why this is not working. So then we just learned previously. Okay, so one thing that really helps to kind of get your references right is to introduce aliases. And so we did that here. Now basically we have for the different occurrences of orders, we have introduced the O1 and the O2 alias. And but the result for that is empty. So basically we get nothing out of that. And so the problem here is that we are comparing here in the where clause, we're comparing the total price, which is a number, with the result of this subquery select max of O2.total price from orders O2, and and in SQL that works, because what SQL will do is basically you have in the subquery you get back this this table with 1 column and 1 row, and that's kind of exactly the scalar that you're getting. But since we want to deal with nested data, we can't do this coercion. And so right now we're comparing the result of the subquery with a single value, and that doesn't work. And so that comparison basically will, as the comparison itself, it will return null, which means in the where clause, we won't get any result, any records that qualify. So then basically we have learned before, okay, so if you just want values and you don't want records, then you just add the value, select value. So then you just get a single value. But you still get nothing because you still have the issue that you're kind of getting a query result of a subquery, which is an array, and on the left side you have a value. And so the right answer is the last one. And so what that does is that you see that you have the subquery down there, and it gets you the value of the maximum of the total prices. And then because you do have an array and you want to get out one value of the array, you actually need to use the, we need to extract the first item of the array to get it out and get a scalar value that is the actual maximal value, so that we then can get the result that you see on the right. So yeah, as I mentioned before, you know, there's
Till, was there an error in the previous slide because O2 was not defined? Go back to the earlier slide. Ah, here. No. Next one. Yeah, there's no O2 defined here.
My bad. Should say
Okay.
from orders O2.
Okay.
All right.
But it's good.
Rohan is paying attention.
It's good. So yeah, you're paying attention and you're spotting the errors. That's exactly what this is about.
Yes.
Honesty. All right. So as you just saw, right? I mean, it is relatively easy, right, to get to a null, right, or to get to a comparison that doesn't work, because basically we're not throwing any errors, right? There's no validation of the types. There's no schema, right? And so basically, in principle, you can compare anything with anything, but you'll get a null if it doesn't, if the comparison isn't valid. And so that is kind of an interesting way that you need to deal with, right? That the flexibility that you're getting comes with the price of being able to find out where the problems are. All right, yes, so we're here, that was the right answer. All right, so now basically we looked at, we showed you some nesting of data. Of course, we can also unnest. And so we did the nesting by having a subquery and creating a nested list. So here we have a simple query that does some unnesting. So what we want to do here, so we have the orders. And let's start with the from clause. So basically we're selecting from the orders O, and then we're unnesting the items field of an instance of O, and that basically will then flatten out the items. And so what we want to get from here is the order ID, the user ID of the person who ordered, and of course all of the items where the item quantity is greater than 30. And so this is what the result looks like. We got the order ID and the user ID at the top level, and then basically we unnested the items array, and from that got the product ID and the quantity of items. So so this is one way to express that you want to unnest a nested array, and a kind of I think more elegant way of writing this is to just, instead of having the unnest keyword, just use a comma. So what we see here is we'll have a left correlation between the orders and the from clause, and so the orders O on the left side is exactly the same O that you see on the right side, right? Basically, those are not independent scopes. And we're using the same iteration variable here to basically take the order and unnest the order or unnest the items from the order. Okay, so if you're talking about sets or collections, you also need to talk about quantification. So what we can do here is obviously, the usual things, so to speak. So if you want to find out if you have an array and you want to find out if any one of those items has a selling price more than 80 in this case, or is an expensive item, so to speak, you can just basically have this, the where clause has this new predicate, which says some I in o.items satisfies that the selling price is greater than 80. So that basically says this predicate is true if you have one item in there, at least one that satisfies this predicate. And of course, you also have the other side where you have a universal quantification, where you require that every item requires that, and that it satisfies a certain property. And in this case, it's that the selling price is greater than 70, and then you also get a result for that. Of course, if you're doing that, then you also know, so there is the option that actually there are no items in there in an order, so that's theoretically possible. And in that case, of course, the universal quantification would be trivially true, right? So you would just get it true because you have nothing in there, so which is probably not what you want. And in that case, you need to have another mechanism to make sure that those items don't qualify. And so a simple way of doing that here is to just count the number of items, and if they're greater than 0, then you know that you're on the right path, and otherwise you might not be. In this case, we're getting the exact same result because our orders all have line items in the data set, so you're getting exactly the same result as above. All right. So one more interesting thing in terms of looking at the composability. So we had this wonderful query. It gave us all of the user IDs, but now we want to have the user names. So basically we can resolve that very easily. So we just take this as a subquery that returns all of the user IDs, and then at the bottom you see the query that gets the name from the user's data set whenever the user ID is in whatever the collection is, and here the collection is what we just determined by that subquery. And so you see it's nicely composable and makes things easy to describe. All right. And okay, so yes, we also have a result for that in your current data on your instance. All right. So let's come back to what Mike talked about before about the data and the fact that you sometimes have fields and you sometimes don't have fields, and so this is one of the properties that we have in the JSON data model, right? I mean, you can just not have a field, even though you could also have a null field, but so basically both are options. And so you need a way to deal with that. And so let's look at a query that helps to illustrate that. So we're going to the orders data set in the from clause, and from that we want to get all of the orders where the total price is greater than 150 and that don't have a fulfillment type, or whether that's not fulfilled yet. And so the way we can express that is that we say, time_fulfilled is missing. So basically, if a field is not there, then we can refer to it as missing. And missing actually is a value in the data model right now, or not right now. It is a value in the data model. And so what you would get here, you're selecting all of these 5 fields, right? And of those five fields, actually one is missing. And so the result that you're getting is that you're getting all of these records, and they actually only have 4 fields. So the one field was missing, and but you asked for 5, right, in the select clause, but you're getting 4 because 1 was missing. And I can kind of explain how that is happening if I go back to the analogy between the select clause and the select value with an object constructor. What is happening is that when you have an object constructor that constructs an object out of field names and values, and the value is missing, that basically cancels out the construction of the field in the object itself, right? So basically we have this red O time underscore fulfilled in the object constructor in the select value, and the fact that it's there basically ensures that the construction of the object will only construct 4 fields because 1 was missing. All right, and so then, yeah, so that's exactly the same result as before, just for the object constructor syntax. All right, and then of course you have the other case, which is so you had a missing field, but you didn't really want to have a missing field in your data, and so now you need to deal with the fact that there's a missing field and you want to put something there, and that is just very simple. We just use the case statement that's available in SQL right now, and in this case, we can determine that the field is missing, and so if the field is missing, then it gets the field value TBD, and otherwise it just gets the field value that was available. And that's what the result looks like. We just replaced the value with TBD, and now we got 5 fields here. All right. Time for the lab. Time for the first lab. So we were thinking that we would want to have about 10 minutes time to do that. And we're actually a little late. Okay, so maybe, okay, let's try to speed this up. And so we have, so we have 10 minutes time to kind of work on these queries. And so we have 5 queries in here, and we'll just leave them on the screen for now. And now I would ask you to kind of go in and write those queries if possible. So most of them are very SQL-ish, so that's probably, yeah. So, yeah, I could read them out, but maybe it's better to just read them yourselves and look at it and maybe give it a try, and then we'll see how that goes. And
so the thought here is that you can also, if you need coffee or you need a quick break, you can take that and then come back, but you're expected to try some of these queries. And you may be wondering, like, what are the angle brackets about? This is a little stylistic thing we picked up from Dan Suchu at Washington. When he gives students queries, he tells them how many results they're going to get. And so you're on the right track if you get the numbers of results that are listed here. And so it doesn't necessarily mean you got the right data, but at least you're on the right track. You got the right number of answers. Your where clause is probably right. So those are like just little hints you can use as you play. And I guess we should resume at what, till 11:30?
yes, let's do that.
All right. So playtime.
Playtime.
And if you have issues, if something goes wrong, again, we'll be watching the chat. We'll be watching the Slack, and just let us know that something's going wrong. And we'll be using remote proctors to make sure that no one's cheating. I guess one other thought is if you're having trouble with something and you have a question, especially if you think the question might be kind of general, go ahead and unmute yourself and ask those questions, and we can also try to answer your questions in real time. I'm going to step away for a minute, but we have a whole handful of people here, and so someone will be listening and answering your questions.
Yeah. And so Pedro was just asking for the yes, and Ian is getting to the schema. Yes.
Hey, I was wondering if I can have a question. I'm trying to just get one row. Can you hear me?
Yes, yes. Sorry, I was just muted when I replied. So,
so I was just trying to get a single row by typing this. I'm gonna chat. Whereas I received the error that you pointed before in the presentation, which is this.
yes, so I think there is. So if you're trying to unnest a name, right? But yeah. The name is a scalar value. So name is just a string.
Name is first and last. No, it has string, two strings, substrings.
Yes, but so good point. So it comes and so the unnesting is about collections, right? So because you can just navigate into objects, but if you basically if you have an array, then you actually unnest, and I should just turn on.
I see. Okay, yeah, got it.
Right? And so that's kind of how that's why if you don't have an array, right, then there's the unnesting doesn't work.
Got it. Thanks.
So for that one, you could say, rather than, you could select star, then you could just say where u.name.first equals boundary.
Okay.
So you can just like path your way, drill your way on through. We have our teaching assistant chiming in on the chat. The only thing is he's not used to dealing with less than 400 people, so it's a small scale class for him.
So maybe we should.
Yeah, I think we should resume.
We should resume. Yes. All right. So,
and people are encouraged to keep playing, but.
So just basically, I mean, we have so this are kind of the solution, so to speak. I'm not sure how much deeper we go. So the first query was about basically getting you the first names of all the users that have placed orders with a total price of greater than 500. And we only wanted to get a list of strings, which is kind of the use of the value, right? Select value to get just the values. And so, yeah, so the corresponding query you can see down here where we're basically taking the users and the orders, joining them on the user ID, and basically choosing orders that have a total price of greater than 500. And for the user that we have in that join, we'll take the first name, u.name.first will basically drill down from the user to the name field and then to the first field. Right, so I think that's relatively simple, at least once you see it written. I mean, that's the big difference. Then the next one was basically get the names and the addresses of stores that have a stock of at least 45 products with wafer in the name. And so to do this, we'll basically need the three data sets, the stores data set, to get, what do we need it for? Yes, to basically get the name and the address, right? That's what we need, the stores data set. Then we need the stocked by data set to determine which store has stocked which products. And then we need the product data set to be able to limit the things that are wafers. And so if you look at the where clause down there, we have the join criterion between the stocked by and the store, and between stocked by and the product. And then we have the product name being like wafer to to get the right products, and then we're getting the query, the quantity that's stocked that needs to be greater than 45. So yeah, so I don't know, did anybody get to the third one? So
I think what we could do, maybe in the interest of time, is to we'll leave these with you as the answers, right? So that don't look at them, go back a couple slides and try them. And then, look in the back of the book, and the back of the book is here for you. And so we'll also make the deck available. But these are all things that you can, I guess, still, if you want to point out any particular things, but I would say we should probably
basically
keep going.
We wanted to kind of show the features in Q4. We will see basically the existential quantification, but I think in the interest of time, I think moving on is probably the right approach. All right, so basically that was the first piece. The first piece was kind of just the basic SQL versus SQL++ comparison, and now basically we'll go one step further and go to looking into what happens with aggregation and grouping, because that is actually quite interesting in the language. So as in the previous part, you can basically have something that is real regular SQL. You see this query, we're taking the stores and the orders, and again joining them on the store ID. And what we want to get is we want to get the count of the orders that we have for each state, right? And so we want to get the count star of that and for each state, and so we're running that on this data set, and we get a result as you would have expected. So we're having actually it's 47 states in the data set, so that's the reality. It's not 50 right now. And for each of those, basically, we get a count, right? And this is regular SQL grouping and aggregation. This is all very nice, but it's the fact how this works, how grouping and aggregation works in SQL is actually kind of hard to explain, because you cannot really split the work up. You can't really represent that in SQL's flat data model. And so grouping and aggregation always go together to kind of get from a state where you're in a flat model to coming to a state where you're in a flat data model. And so what you usually do to do that, to explain this, and that's what I learned from a teacher of the arts, is that you create a different representation of this, that like the one that we have here, where basically you really explain that you have the different states here, and for each of the states, basically you have a store and you have an order, and you basically have these groups, and within these groups, then on those groups you can actually do some aggregation. And so yeah, so this is a little bit, it's a little bit hard to explain. And so in SQL++, that's actually better. So let's take a step back and see how in SQL++ you can actually separate grouping from aggregation, so you don't have to do it all in one go. So first, on just looking at SQL++ aggregation only. So what we have a query here that where we want to get the email and the number of items in an order. Yes, we want to get those information, and we want to get that for the 3 largest orders that we have, and the size of an order is defined as the number of items we have in that order. And so you see here in this query, what we'll do is we will do our join, and then we will get the email, and we will simply get the array count of the items. So the items is a nested thing, is a nested set. And we'll just get the array count, and then we just got a very nice aggregation of that count, right? With a simple function call, which just is you pass in an array of items, you count them, and it's all very, very simple. It's just a simple function call, and you get a result where you see that Claire Evans had an order that was of size 8, and you can see the other ones. So this is all very simple. Now, if you look at how you would actually express that in SQL, that looks quite different, right? If in SQL you wanted to get the max of a list, like in this example, you would select the value max of the list price from the products. You would have some word clause there to make sure that you only get numeric values, so because you might have dirty values in there. And then we would determine the maximum based on this parameter that you get to the max function, which is the list price, but it's actually not the list, the parameter that goes in, it's actually the column that you're actually aggregating over, right? And so if you wanted to write that in SQL++, you could actually have a much simpler way of doing that, which is you just basically do as you would think about it. You would take the list prices from all of the products. You first get all the list price from all of the products, and then you simply take the sequence that you just produced and put it into the array max function, right? You basically have the parameter, you put it into the function, and you get the result. So basically there is a very simple aggregation that's happening here that does not require the SQL magic. And you will, of course, get the same result. All right, and so similar to being able to do aggregation only, in SQL++ you also can do grouping only. And this is, I think, really interesting. So what we want to do here is show you kind of how you can actually look at groups, right, that are materialized using the query language. And you can do that using the group as clause. So that's a new clause in SQL++, and which allows you to basically bind a variable name to the group that you get. And so if you were to run this query, the result would look like this. And it's kind of big. But you will see that if you look at the select clause, there's basically, we're selecting the group key, right, which is s.address.state. And so you will see in the result in the violet color that's the first kind of column of the object that's coming back, or the first field, which is Arkansas in this case. And the second thing that you're selecting in the select clause is G, which is the whole group. And the whole group that you can see here, that consists of an array of objects, and the objects that you're getting are what do I call them? Are the stores and the orders that we have, basically the pairs of stores and orders that we're getting from the from clause, right? After the filter. And so what you see here again is it's similar to what we have for select star, right? We have this nested structure, and basically for each of the variables that goes into the grouping, we have a field that contains these objects, and you basically can now really describe the whole group. You have the whole group materialized in here as the sequence of pairs of stores and orders. So basically, we can get full grouping. And so right now, what we did here, we gave you the whole group, right? And the whole group is a little bit unwieldy, right? You can see that it's a lot of things, but you can basically run a query or a transformation on that and get the subset that you care about. And so, for example, in this case, we have the same start. We're taking the stores and the orders, and we're joining them, and we're grouping them by the state. But instead of getting the whole group, we just get a subset. Basically, we run a query on that group. And so in this case, we're just getting the store ID and the store name and the order ID from that group, and get a very sensible result of kind of understanding what those store order pairs are. So you just basically, right now you get these groups and you run a query. And so here basically you have one group for the state of Arkansas, and then basically you get all of the store and order pairs, and basically can really reason about these things. And coming back to what we had in the beginning, the question of, okay, so how do you explain grouping and aggregation, right? I mean, how do you bring back the grouping and aggregation that you have in SQL to what we can do in SQL++? That's basically with a very simple query, right? And what we do here is that it simply taking the group, right? The groups, basically you will have the group variable. The group variable will contain all of those pairs. And then you just count whatever is in the group variable. And that will be exactly the count that you get, the count of the orders that you get for the state. All right. I hope that somehow made sense to kind of separate these two and reason about them. So basically what we do is that we can, those groups really are that intermediate representation that's kind of missing in the flat world because you cannot express any nesting. All right. And we have a second lab.
So this is another chance to exercise AsterixDB. I think maybe in the interest of time, we should cut a little time off this lab. So we were planning on giving you 10 minutes, but you still have your coffee from your last break. So maybe you don't need all 10 minutes. 5 minutes for coffee, 5 minutes for queries. You can just do 5 minutes for queries. And so maybe what we should do is let you look at this and maybe play around. We'll give you 3 queries, but pick one and play with that query. And again, we'll come back and we'll sort of let you know how to find the answers in the slides. Does that seem like a good plan? 5 minutes, Till?
Yes.
All right, so we will resume at 11:48 according to my machine's local time.
Yes.
So 5 minutes from now. And again, feel free to chime in with questions, even vocally, right? Because we forgot that soundtrack that we should have had for the labs. Some Kenny G music or something to, maybe something that would keep you awake. feel like we're proctoring a UCI exam. We're about halfway through, so you should check your time. Hopefully making progress on your queries. Again, you will get 100% if you get one query right. So the other 2 queries are extra credit. You can pick any one of those.
All right, I think we should resume. We passed the 8:47 mark. Okay, so let's take a quick look at the queries. So the first one was list the names of users that have placed exactly 14 orders. And so yes, what we're doing is we're joining the users with the orders, of course, on the user ID. Then we group them by name and having the right count of 14, right? Because we wanted to go for exactly 14 orders. So this is basically a really SQL query. There's nothing SQL ++ specific around here. So the query 2 was that we would like to get we want to get the category and the number of stores containing categories for the 2 most frequent store categories. So we would just want to find out, right? I mean, what are the most frequent store categories and how many are there in those? And again, so we need to do some unnesting. So basically it's all based on the stores data set. And then, so inside of each store, we're unnesting the categories. So now basically we just have the categories, and then we group by the categories and group basically the stores by the categories, right? And then we order them, we group them, we count them, and then we order by the count. And so which will give us exactly the top 2 ones. And so this basically has some SQL specifics because you need to use the unnesting that's available. And the third one is
question in the chat.
Sorry?
So we have a question in the chat that I think is a good question. I was thinking the same thing, which is that our answer to the first query, this is a good catch, assumes that without evidence, that names are a key, right? So the names are unique. So it's the users. So that's, yes, good point. Sort of the assumption here has been that names are unique. The other, I guess, the one other thing that's sort of interesting is name as a struct, right? Name is a 2-part thing, and you're able to group by that. So that's a little bit of a SQL++ thing that looks like a SQL query.
Mike,
but it's doing.
I didn't know the schema, so I wasn't sure whether the orders were all individual orders or they were actually a nested set of orders within the username. In which case, I was going to ask why group by is needed at all.
Yes, so users, so the from clause has shopalot.users and shopalot.orders. Those are both collections. And so it's a sort of a separate topic, but good database design for NoSQL still gives you a bunch of collections, right? Because you still kind of want your entities to be objects and objects to be in collections, and things like items aren't entities, so they go inside orders, but that's a longer discussion.
So you are saying you have separate orders. I mean, for each order of a user, there is a separate object?
Yes.
Okay.
Yes, because if you think about your Amazon, or at least my Amazon shopping history, I would not want all of my orders forever to be inside my object, because my object would have exploded quite a while ago, especially during COVID times, right? So, so you still want to keep these things separate. So you'd have users and orders, but line items, they don't deserve to be orphaned, right? They deserve to be inside orders because they're just nested content of orders, right? So you get, there's still things that look, very kind of relational in the sense that you have a number of collections. But then when things are naturally go inside something else, if they're kind of a bounded thing, like my list of, pet names or something like that, those can be inside. But there's a whole separate probably topic about, proper NoSQL database design.
Thanks.
All right.
We got the last one. I think we'll skip over that one and move on to the next topic. All right. And I think I will stop sharing for that. Over to you, Dimitri.
All right, thank you, Till. Let me share my screen. You can see my screen, right?
Yes.
Yeah, okay, good. All right, so I'm going to talk about advanced analytical features of SQL++, grouping set and window functions. And then we'll have our third lab exercises on these topics. So both features have been supported in standard SQL for a while. So grouping sets were introduced in SQL 99, and they extend group by clause to allow aggregation over multiple sets of dimensions. And window functions appeared in SQL 2003. So these functions allow aggregation over windows computed on the input data. So we do support both these features in SQL++ and in our most recent release of AsterixDB. So we'll start with grouping sets, talk about rollup and cube modifiers, and go over some examples using those. Then we move on to various window function calls. So let's look at first at the following query. So we would like to count the number of stores in each city, in each state. And to limit the result, we would only consider states with names starting with C. So just California and Colorado. So in addition to count by city, we would also like to get a total count by state and the overall count of all our stores. So how do we do that? So one way of implementing this would be to have a union all over 3 subqueries. So the first subquery would group by state and city, the second would group by state, and the third one would just do select count star over the whole data set. So that would work, but requires a lot of code duplication. So with grouping set, we have a better way. So we can simply use a rollup modifier in the group by clause. So if you look at the box on the right, you'll see 3 different formulations of the same query. So the main element here is the grouping sets modifier in the middle, which provides a very compact way of specifying those unions. So each grouping set is logically expanded into a separate subquery, and they're all connected by union all operations. So of course, this is just a logical way of describing the result. So the query processor is free to optimize the query. In some cases, could find a faster way of computing the same result without subquery expansion. So the grouping sets modifier is a shortcut for union all, but the rollup modifier is a shortcut for grouping sets. So rollup with n elements is expanded into n+1 grouping sets, so rolling up to the grand total. So in our query, we start with a rollup with 2 elements, state and city, and therefore it would expand into 3 grouping sets. So one would be city and state. So the second one would be the whole state, grouped by the whole state, and the last one, the third one, would be a grand total. And that's exactly what we want in our report. Now, if we look at the query results, we'll see that we have black rows that correspond to grouping by city and of course state, city state, blue ones for the whole state, and the single red one for the grand total. So cube modifier is slightly different. It's a relative of rollup, but performs a slightly different expansion into grouping set. So in this example, we want to find out our total sales by each year within each state. In addition to that, we would like to roll up by year, but also roll up by state and get a grand total. That's what the cube modifier is for. You can roll up by multiple dimensions. So in contrast with the rollup modifier we discussed earlier, which can only roll up by single path through the dimensions. So if we look to the cube expansion on the right, we'll see that given n elements, it produces 2 to the power of n grouping sets. So for 2 elements, it would produce 4 grouping sets, and for 3 elements, 8 grouping sets, and so on. And recall also that each grouping set is logically equivalent to a union all subquery. So the cube modifier saves us a lot of typing. So as for the query results here, in black color, we would get total sales grouped by state and year. So green color only grouped by state for all years, and blue grouped only by year for all states, and the single red row for the grand total. Right, so now let's turn our attention to window functions. So window function calls are widely supported by all major database systems. So they provide a concise way of specifying aggregations over logical data partitions and windows over those partitions. So let's start with a simple window function call, computing ranking over the whole data set. So we'll use the rank function for that, followed by a over subclause. So this subclause indicates a window function call. And inside that over subclause, we're providing a order by clause to specify the ordering condition within a partition. Now, window function evaluation in this case would be as follows. So it's a simple over clause. So first we need to establish the input tuple stream. So as we mentioned before, our product dataset contains a small number of non-numeric values of the list price. So first we need to filter those out. That's why we have that where clause. Then we start processing the over clause. So subclause. So we order all input tuples by the list price from greatest to least, because we have a descending modifier in the order by specification inside the over clause. So then we would go through those order tuples one by one and assign the rank incrementing from 1. So if a tuple has the same list price as its predecessor in the partition, then we do not increment the rank. So we skip over that rank value until we find the first different non-equal successor. So that's why if you look at the results, you see there is a jump in the rank from 5 to 10 of the last item, because there were several products with the same rank. So the previous query was computing the rank over the whole dataset. But what if our goal was to establish rankings within each product category? So we could also do that using window functions by using the additional clause, which is a partition by. So partition by subclause instructs the query processor to partition the whole input tuple stream into non-overlapping logical partitions, and then evaluate the window function independently on each partition, ordering partition tuples before computing the function. So as you can see in the query result, in this case, we have multiple products with rank 1, because we started from that value in each product category. Recall also that the rank is the same for products with the same list price. That's why we have 3 top ranked beverages in the result. So logical data partitioning performed by window functions gives us a flexible way of filtering data within those partitions. So in this example, the rank is computed by the subquery and used by the main query to return only the top products in each category. Notice that the subquery is written using a common table expression using the with clause. So this is another SQL feature that is also supported in SQL++, because common table expression are very useful. So they make queries modular, easy to write, and debug. Now, as you can see, we have query results ordered by rank, and we only get top ranked products in each category. So far we talked about special window functions like rank, but any regular aggregate function can also be used in a window function call. Aggregate functions, however, need a list of values to operate on. So therefore, when an aggregate function is evaluated in the context of a window function call, there is an additional subclause in the over clause that defines the frame of tuples for it to process. So you've probably seen this before in SQL queries. The frame specification starts with like rows or range, and could be bounded, unbounded, and preceding or following. So it is optional, and if not specified, then there is a default one that would be used, and we'll see that later in this example. So we support exactly the same frame specification as SQL does, and also have the same default. So users that are familiar with SQL can start with using window function and SQL++ right away. So when there is a frame clause, or if there is a default frame clause, basically when an aggregate function is computed, then the evaluation steps are then augmented by the new frame computation step. So the first 2 steps, they remain the same. So the input stream is logically partitioned, and then tuples are ordered within their partition. And each partition is processed independently on others. just wanted to note that AsterixDB is able to process those partitions in parallel, because it's a parallel database if the system has enough resources. So the evaluation starts at the first row of a partition and computes a frame of tuples for that row based on the given frame specification. So interestingly enough, just to note that the frame may or may not include the row itself, because the purpose of that frame is only to provide the input to the aggregate function. So then the aggregate function runs on that frame and computes the result, which is added to the output. After this, the query processor moves on to evaluate the second row in that partition. So the frame is recomputed again for the second row, and the aggregate function is reevaluated on that frame, producing the second result value. So then the evaluation moves on to the third row and so on until the whole partition is processed. The frame specification syntax is quite elaborate and gives plenty of room for query optimization opportunities. So for example, a frame could be static, so its contents doesn't change from one partition row to another. So some frames could be sliding, and while other frames can have fixed starting point at the beginning of a partition and just keep growing within a partition. So this variety allows the query engine, the query optimizer, to employ different and optimal execution strategies for different shapes of frames. So now coming back to our example. So there is no frame specification given in the window function call here. So the sum function will use the default frame specification. And the default is same as in SQL, is a range between unbounded preceding and current row. So, but this frame corresponds, the shape of frame corresponds to a running total computation. So the query intent is to produce monthly sales in the year of 2020, along with the running totals. And in order to achieve that, it first aggregates sales by month, and then uses the window function call to compute running totals over those aggregated values. And one more quick example before we start our third lab. So this is just wanted to show another very common analytical query. So we would like to in this example, we'd like to produce a report showing our annual sales growth broken down by quarters. So in other words, so we want to show how our sales are doing each quarter this year as compared to the same quarter in previous years. So what's the sales growth compared to previous years? So in order to produce this report, first we need to aggregate orders by year, by quarter within each year. That's what the subquery is doing. Then it's time to apply a window function on top of those aggregated values to compare each quarter with its preceding quarter from the last year. So the window function we'll use is called lag. It's not an aggregate function. So it operates on the whole partition, and it basically provides an access to a previous value in the logical partition, which is produced by the partition by subclause. And the previous value would be according to the ordering imposed by the order by subclause of the overclause. So and that's exactly the kind of function that we need to solve a problem. So we partition the subquery results by order and order by year within those partitions. So then we use the lag function to access the previous sales value, which is the quarterly sales in the previous year. And once we have that value, so the rest is straightforward. And one more note is that if you look at the query result, you'll see that we have a null for the first sales growth number there. So this is because we only have sales data starting from 2019 in our data set. And the lag function, the semantics of the lag function, that it returns null for the first row in each partition, because there is no previous row in that partition. So hence our growth computation expression also returns null, and we get basically null in the query result. So I guess if there are any questions, I could be happy to answer them right now before we move on to our third lab. All right, then let's do our third lab. And again, I think the intent was to have 10 minutes, but Mike, please correct me if we need less time here. But the idea is, the assignment is to create 2 analytical reports. So the first one is called Q1, and the query should produce sales by product category each year. So in addition to that, the report should include total sales for each category across all years and the grand total of all sales we have in the database. And the expected result is shown below. Basically, so you start with a grand total and then roll up by product category, and then break down by individual year. And So the second report we need is Q2. It's called Q2 and has to do with running totals. So we'd like to analyze monthly beverage sales in California in 2020. So each output row for that second report should correspond to a month and should show monthly sales and running total of sales. And also note that these are advanced kind of queries, analytical queries. And if we were grading this assignment, we would give 100% just for a single query and a bonus point for the second one. But we're not grading, so anyway, so I guess if there are no questions, let's get started. And
I would say in the interest of in the interest of time, I think we're supposed to end at 12:30, and so we're a teeny bit behind, but not too bad. So let's do 5 minutes here and just try one of the queries, and then at the end of the 5 minutes, we'll show you the results, and you can sort of go off and try them on your own if you want. You can mute looking at us while we show you the results if you don't want to see the answer ahead of time. And to make it easy to know when to restart, 5 minutes from now is 12:12. So we'll resume at 12:12. Easy to remember. And we'll see you back here at that point. Speak up if you have questions. And there are probably two kinds of people in the audience. There are people like me who are academics to whom, this was like for business people, right? So I didn't really know this part of SQL as well. And so for those of you who are new to this, you may find this a little bit harder. For those of you who are, sort of SQL analysts, you're going to go, okay, it's 12:10, now what? All right, so we'll see how it goes.
While people are doing real work, can we have some chat about where SQL++ is in terms of adoption and so on?
Sure. So basically, SQL++ kind of originated. The history is from UC San Diego. And so Janis P. Basically designed it. We had our own language called the Asterix query language, AQL. And we would, it was based on, sort of X query. And we would always explain to people why SQL was inappropriate for semi-structured data, and they should therefore be thankful to us for this wonderful X query-like language. And they would always kind of tilt their heads at the end of those presentations and go, yeah, I get it, but I really like SQL. And so Janis spent quite a bit of time thinking carefully, like in the project, he was doing a mediator that was dealing with different kinds of data. And the mediator wanted to deal with semi-structured data, but how could I extend SQL? And so, we kind of quickly went, okay, so great people invented X query, we'll just kind of simplify it. And he thought long and hard about that. And so he designed this language and he came back and showed it to us. And we went, yeah, that's what all these tilted heads were actually looking for. So then we became kind of a prototype. He built a reference implementation. I think it was memory-based. We built a reference implementation. We said, okay, we're going to take that and try it in AsterixDB. And then we tried it and we liked it. And we said, okay, we actually, in most recent release, said, okay, there is no AQL anymore. We deprecated it. It's SQL++. And so that came out of work that Janis did. And then Couchbase, which has a product offering called, Couchbase Analytics, speaks SQL++. Couchbase, and they have a query product that also speaks that. It's called Nickel, non-first normal form query language, which I think is one of the cutest query language names I've seen in a while. So if you hear people talking about Nickel and Couchbase, it is also this language. And then Janis kind of moved on from UCSD for a while. I'm not sure if he's back or not, but joined Amazon. And so you will find a very close cousin of SQL++ also at Amazon in a language called Particle, which I think is in Redshift's Spectrum and some other places inside Amazon. So this language has got some dissemination. There is no standard, right? There's no ISO, there's no ANSI for this.
That was going to be my next question.
Yeah. So right now there's not like an effort going on to try to do that. But you'll find it or close cousins inside, the open source system that everyone clearly wants to have, but also, in commercial products like the Couchbase products and in Amazon interfaces and so on.
Thank you. I see. So the Microsoft guys haven't chosen to do something like this, huh?
No, but if you look at the Cosmos DB query language, they do have kind of a single table version of it that looks strikingly similar. I'm not sure, if there's any intellectual, descendancy, or whether just the single table version of it is obvious and therefore everybody would do the same thing. But you kind of look at what you can do with one collection in Customer DB. Again, it's very much like what you see here.
Mm-hmm. Great, thanks.
Yeah.
Perfect timing.
Yeah, I think it's 12:12.
Yes.
Let's check our answers. All right.
So Mohan, do you want to Mohan screen share your answers first?
So yeah, just kind of a few notes here. So the key ingredient in both reports is getting access to line item data for each order. So because each line item contains a product code, so which could be used to fetch the product category from the products dataset. So line items are, as you remember, are stored as an array inside each order. So that's why we need to use the unnest clause to iterate over those arrays and unnest them. And the remaining steps for the first query are relatively easy. So we join now, after unnesting line items, we join with products to get product categories for each line item. And then do a group by with a rollup by category and product category and year. So the first report is now complete, and we can look at the second one. So we know how to get, for the second query, we know how to get product categories, but still need to figure out how to get the state where the sale happened, because we were only interested in orders from California. And so obviously, if we look at the store information, the store fulfilling the order has an address, so we can get a state from there. So for that, we need to join orders with stores dataset to get the state information. And before doing running totals, we need to aggregate our data by month. And once we have that aggregated data, then we use the sum function in a window function call to compute the running total of sales. All right. So I think we're done with exploring advanced analytical features of SQL++. And so we're going to move to the next topic, which is our supporting data science use cases with AsterixDB and SQL++, and I'm handing it over to Gift.
Thank you, Dimitri. I can share my screen. Okay, so next I will talk about our support for data science use case. So part of our inspiration comes from looking at data analysis workflows. So our understanding of a typical small data analysis workflow is we have a data scientist who develops some sort of machine learning model and data analysis pipeline using Python. Running that locally on a laptop on top of a small data set produces some results, which the data scientist will evaluate and oftentimes make some adjustment to the machine learning model, rerun it, reevaluate the results again. This is an iterative process that goes on until the data scientist is satisfied with the model's performance. And at that point, the model will be transferred to run in a production environment. So to go from small to big data analysis, the locally constructed model and the pipeline will be handed over to a system engineer or a data engineer who will have to reconstruct the model, translate the pipeline using a distributed library syntax like PySpark and MLlib. He'll then have to set up and maintain a distributed compute engine and storage to be able to handle the massive amount of data. Running this newly constructed pipeline on top of big data produces some results, which eventually be propagated back to a data scientist who, upon looking at these results, realizes that he has to make some adjustment to the machine learning model. So the cycle continues. So problems with this workflow are that there could be errors when translating the algorithms, and each iteration could take days, if not weeks. So our solution is trying to reduce the turnaround time by eliminating the need to translate the algorithms and set up several distributed systems by leveraging Apache AsterixDB and wrapping the locally constructed pipeline as a user-defined function, allowing data scientists to interact with distributed data the same way that they would with locally stored data. So next, I will talk about our setup for the demo to show you how you can use a locally trained machine learning model in Apache AsterixDB. So here to the left is a label Twitter sentiment data about US airlines that I obtained from Kaggle to use as our training data set. It has 3 different sentiment types, which are positive, negative, and neutral. To the right here is a Python code that generates a simple sentiment classifier that I trained on the Twitter dataset. So this example uses the scikit-learn library. So here, my input to the model is the Twitter text, and my output is the sentiment type. So I created a pipeline that consists of 3 components. So first, it counts the number of times each word occurs in the training data, and then convert that into an invert term frequency matrix, and then applies the logistic regression model. So this is just a very simple pipeline construction, just to show you an example how you can train your model and then use it in AsterixDB. So what is important here is the last line of the script. So here, after I have trained my model, I use the Python pickle to save it as a serialized package called sentiment model, which I will then deploy to AsterixDB. So if you follow the arrow here, it points to my Python wrapper called sentiment.py, which I use to register my scikit-learn model in AsterixDB. So here I create a class called model. An instance of the class will load my scikit-learn model. So the class has one method, which is getSentiment, that calls the predict function on my scikit-learn model, given an input text. So next here, so after I deposit my model, what I'll have to do is I will have to create a function so that I can call it in my queries. So the function name is getScikitSentiment. So the text in red refers to the model name of the wrapper, which is sentiment.py, and the text in blue refers to the method, including the class name. So I will be showing you a demo on the Yelp open dataset. The dataset contains information about users, reviews, and businesses on Yelp. This is the types that I use to create my 2 datasets, businesses and reviews. I will talk about them in more details when I show you the demo. So now I will switch over to the demo. Okay, so back to our AsterixDB user interface here. So I have preloaded the 2 datasets. The first one is businesses. So for businesses, we have access to business ID, which is unique for each business. We have access to the name of the business, the location, other attributes about the type, and we also have access to the type of the business, which is called categories. For example, this particular one is a Mexican restaurant. And another data set is called reviews. So for reviews, we have access to review ID, which is unique for each review, business ID, which is what business this review is directed to. And we have access to the text of the review, user who posted the reviews, and other logistic about this particular review. So let's say now I am interested in going to a pizza restaurant. So what I would do is I would then query the business's data set on the categories field. So here it's just a very simple query to get me enough information to do my analysis on. So I filter. Either it contains the word restaurant pizza or pizza restaurant, basically a restaurant that sells pizza or a pizza place. So here I project out the business ID, name, categories, the overall rating of the restaurant, and the location of the restaurant. So now for easy access, I will save it as a new data set. So I can query it just by querying the data set and not having to write the query, the selection query. So what I'll do is I'll do an insert into a new data set called pizza restaurant. It's running that. So now just to show you the results, the data set contains the exact same fields that I just projected out before. It's just now saved into a new data set for easy access. So now I have access to my pizza restaurant. What I would like to do next is I want to get reviews about these restaurants. So what I'll do here is basically I am joining the pizza restaurant dataset with the reviews dataset on the business ID field, because I know that business ID is unique for each particular restaurant. Joining them on business ID will get me reviews about each particular restaurant. So here I am projecting out review ID, business ID, text of the review, the star that user gives to this particular pizza place, and the name of the place. So I also put this dataset into the results of the query into a new dataset, so we don't have to wait for the joy every time we want to get pizza reviews. Just to show you that this contains the exact same information, the exact same attributes. It just now saved into a dataset called pizza reviews. So at this point now, I would like to know about the sentiment. I would like to apply my sentiment model on the pizza reviews. So what I will do is, like I said before, I have pre-deposited my scikit-learn train model, and I created a function called getScikit-sentiment. It takes in the text and it produces a sentiment type. So here, given it 3 sentences, you can see that it produces 3 results. Each one corresponds to the sentence in the array. So the first one, something that's good, gets positive reviews, and so on. So at this point, I can actually apply the getScikit-sentiment on my pizza review dataset. So now just to show you that, here, I am applying the scikit-sentiment model to my pizza review and projecting out the text, the name of the place, and the sentiment that the model produces. So far so good. Something that's clearly positive gets positive. Something that's negative gets negative review. So at this point, I can actually filter using the name. For example, let's say I'm interested in a particular pizza place or a particular chain. For example, Pizza Hut. I can do a selection by name and then apply the model. So here are 5 reviews about Pizza Hut. So that's basically what it produces. And let's say now I would like to get the overall count of how many positive reviews is it getting, how many negative reviews is it getting. So what I can do is I can actually write a group by query, but even better, I can create a function so that I can call back to it in subsequent sessions. So this function is basically taking in one parameter, which we map to the name of the restaurant. The body of the function is basically producing grouping by the sentiment type and getting back the count of that sentiment type. So running that. And now what I can do is I can do select value from my get sentiment count function, given the name Pizza Hut. So this will get me basically the overall count of each of the sentiment type that the model produces for Pizza Hut. So you can see that the model thinks the majority of the reviews fall in the negative category, but we also have to keep in mind though that probably most of the reviews are not completely 100% positive or 100% negative. Sometimes people give things that they like about a restaurant and things that they don't like about a restaurant, but there's only one result that the model can produce. And also this is a very simple model just to give you an idea of what you can do with use of the five function. But if you want to go further, let's say you want to see what the star ratings are, instead of grouping them by the sentiment, I can group them by the actual stars that people give to each review just to compare and contrast how my model perform. So, just grouping by the star, you can still see that majority of the reviews fall under 3 stars. So maybe the model isn't that bad and there could be some compare and contrast you can do with that as well. So this wraps up my demo about how you can create your own locally trained machine learning model, package it as a user defined function, deploy it to AsterixDB, and then call it in your queries. So I'll pass it back to Mike for closing.
Mike, you're muted.
Let me unmute, yes, and get ready to screen share again. So that's basically it. So we wanted to leave just a few minutes for questions. Not too many minutes, so you can't ask too many questions, but just to kind of recap what you've seen. So what we've done is to share with you AsterixDB, which is a big data management system. Again, it holds your data and indexes your data. It's a parallel database, right? And so the the thing that you can do with this is then you can store, sort of all the tweets you have or all the kind of big semi-structured data you have, and you can use SQL specifically, to do analytics over that, including all the advanced analytics that you would like to be able to do kind of with SQL and SQL++. System's available for download, so we're showing it to you in Amazon because it's easy to do that, but it's also pretty easy to download, and you can use it if you have applications, if you wanted to do teaching and introduce people to sort of NoSQL done right, you could use AsterixDB for that. If you'd like to do some research things around sort of NoSQL, it's also a platform that could be used for that. And we've got people from multiple universities and all over the globe, really literally, who are involved in that. And so we'd be more than happy to help you get started. One other thing I should point out is that this is a system which I would characterize as being like scale independent, meaning that when you're working on a laptop, if you end up with 20 nodes full of data, the experience will be the same. So we'd be happy to help you get started. You can go to the URL that's listed there. Whoops, didn't mean to do that, hit the wrong thing. And we'll be happy to take your questions at this point.
What's coming up?
I guess one other thing I should mention is basically Don Chamberlain. Yes, that Don Chamberlain has written a book. It's available free on the Asterix website, or Don is a retired IBMer, right? And you might have heard Mohan whining right before this about, once you've retired, IBM stopped sending you checks. And so you can also get the book, from Amazon if you want to, about SQL++. So this is written by Don, who's one of the world's greatest writers about query languages. And then there's also an online tutorial that is listed here that you can go, and that's hosted at Couchbase at the moment. All right.
Not sharing the screen. So
let's see.
My question was, what are you guys working on as the future stuff?
All right, hang on one second. So I just took you through some slides very quickly, I think, that
Okay.
Jill just pointed out I didn't share. So let me go ahead and do that. I'm just going to back up and show you what you should have seen real quickly. So that's kind of our summary slide. That's what you heard me talk through. And this is the URL you can go to get that. And again, you can get this book. You can find it on the documentation link at the Apache site for AsterixDB, or you can find it actually at Couchbase as well. And then you can also go sort of play online with Don Chamberlain data that is inside this book at that tutorial. All right, sorry, Mohan, you had a question.
I was just asking what's coming up next in terms of.
So there's a couple things. So one of the things we're doing is that Gift, who just gave you kind of a glimpse of the future, she's working on sort of data science meets AsterixDB, and so she's actually built something called A-Frame, which is actually a sort of a pandas lookalike that talks to AsterixDB. And she actually presented that at IEEE Big Data and won the Best Student Paper Award. Congrats, Gift. Sort of late last year. And then now working on sort of an extension of that called Polyframe. So now that it also talks to sort of some of your other less favored systems, Postgres, MongoDB, and Neo4j. So you can actually do kind of pandas data science on top of those systems. And so kind of looking at separating with the theme again of making big data feel small. And then kind of in the AsterixDB, there's sort of always ongoing work about, how should you run multiple queries concurrently, and how should resources be managed? How can we make LSM better and faster under the hood? So it's kind of a platform for doing that. And then at Couchbase, there's lots of work in terms of how do we, take and provide this for people who want to write checks for software and would like to be able to do this and have it all work and be supported and things. And so it's also, there's work sort of going on there. And then we also have research branches of this. So we have at various universities, we're doing crazy things. So we're doing work on big active data where you can subscribe to data, and Asterix will, the bad version of Asterix, bad Asterix we call it, will send you data when data of interest is ready for you. We have another branch where we're trying some new dynamic approaches to query optimization. So the system it's like, we're doing core engineering kind of research. We're also doing kind of crazy extension research. And we're also doing, serious, I have NoSQL data, my applications are NoSQL today. How do I analyze that data? Things at Couchbase. So there's a variety of activities going on. So it's a kind of a fun, synergistic project. Other questions? All right, so I think we're 1 minute over, so we should probably let people leave and get their minute back. You'll never get that minute back, I guess, but sorry about that. But we only took an extra minute. So thank you all for coming, and please feel free to sort of continue in the Slack channel, or get a hold of us. We'd be happy to help you play some more and maybe use it for some things that you really actually want to analyze that are NoSQL.